Hello everyone. In this video we will continue to examine topic 12.1, the interaction of matter with radiation, and in particular we will continue to unpack the photoelectric effect. So the final graph we need to be super comfortable with is the graphical analysis of the photoelectric effect experiment itself, and in particular the analysis of the photocurrent versus the applied potential difference. We've already seen this graph, but it is important to recognize what that graph would look like under different conditions. So take a look at number 1 here. This is the photocurrent versus the applied potential difference graph for the same metal or work function, the same frequency of incoming light, but different intensities. And we've partially discussed this before. So recall that for this graph, the general shape is that there is no photocurrent until the stopping voltage has been reached as I move and I go from more negative voltage applied, so more negative applied potential difference to more positive. And then in this region of the graph, the electrons are being slowed down, but there is some photocurrent. And then finally, as we crank the applied potential difference up in the positive direction, we ultimately saturate the graph. That is, we capture all of the electrons that have been emitted in this particular experiment. So now compare what happens if you have different intensities for the same frequency. Well, if you increase the intensity, you're going to send more photons of the same energy each. And because they are the same energy each, the same photon energy means that you will have the same stopping voltage required to stop those electrons. So if they have the same energy, then even if there's a higher intensity, those photons will give the electrons at most the same maximum kinetic energy. And as a result, you will measure the same stopping voltage. Notice that this will depend on the frequency, which we are keeping the same. And then finally, we should note that if you increase the intensity, you will increase the saturation current, that is, that maximum current. That's because at higher intensity, there's simply more photons ejecting electrons, and when all of those electrons are absorbed by the electrode, you reach the saturation current, so the maximum current is higher because more electrons have been ejected at constant frequency and for the same metal. Now, what happens if you have the same metal, the same intensity, but different frequencies? Well, this is probably the trickiest case. Firstly, notice that if you increase the frequency from low to high, the stopping voltage increases. Why? Because at high frequency, those photons have more energy, and because they have more energy, the ejected photoelectrons have more kinetic energy, and because the ejected photoelectrons have more kinetic energy, it requires a higher stopping voltage to completely stop them. So red Vs is bigger than blue Vs here. But the most challenging little concept in this graph is between the saturation currents of these two, and it's definitely a counterintuitive trend. Lower frequency light for the same metal and same intensity will involve a higher saturation current than higher frequency light. And the reason for this is due to the fact that at the same intensity for low frequency and high frequency light, you are dividing up that intensity into low energy and high energy photons. And if you divide the same intensity into high energy photons compared to low energy photons, you will get fewer photons for the high frequency light than you will for the low frequency light, assuming constant intensity. So there are fewer photons for the high frequency light than for the low frequency light. Because there are fewer photons, then even though they eject the electrons with more kinetic energy, okay, there will be fewer photoelectrons ejected for the same intensity. And because there are fewer photoelectrons ejected total, then when that current is saturated, when the applied potential difference is grabbing all of the electrons and zooping them over to the electrode, that saturation current will be lower than for low frequency light, because at the same intensity, the low frequency light will simply have more photons. Although it's worth noting that if you decrease the frequency too low, Okay? If you decrease the frequency too low, then you will get no photocurrent whatsoever. Okay? So eventually, at low enough frequency, no electrons are ejected. It's not enough energy to overcome the work function. So below the threshold frequency, you will get no photocurrent whatsoever. Moving forward, you should definitely make sure you're comfortable with the problems having to do with this particular topic. One thing we didn't really go over, but you should make sure you know how to do, is that when calculating energies of electrons, you will sometimes be asked to find the speed of those electrons, and you should be comfortable applying your kinetic energy formula and converting all requisite energies from electron volts to joules and back again as needed. So be aware that these questions and these questions and these questions are all good practice for the photoelectric effect.